This is geometry lessons 7.7, 7.8, and 7.9. We're going to combine them all into one here. So we're going to be talking about some properties of parallelograms, some theorems that relate to those properties where we can prove something is a parallelogram. And then finally in 7.9, we're going to look at the diagonals of different quadrilaterals and how those can also help us prove that something is a certain type of quadrilateral, like a kite, a parallelogram, isosceles trapezoid, etc. So let's start in 7.7. We're just going to look at parallelograms here. The big idea says the properties of a parallelogram can be deduced either from its rotation symmetry or from congruent triangles formed by its diagonals. So if you get into the weeds of this stuff, all of these properties that parallelograms have mainly come from these congruent triangles that are created when we draw the diagonals. But we're just going to focus on the special properties here that they have. All right, so the properties of a parallelogram theorem is broken down into 4 pieces, A, B, C, D. If you're ever referring to this in a proof, you just say it's the properties of a parallelogram theorem, and then you can specifically list its letter A, B, C, D, etc. You'll see that. All right, so here's the 4 things that are special about a parallelogram here. Opposite sides are always congruent, same size. Opposite angles are always congruent. Consecutive angles are supplementary. Consecutive meaning as you work your way around from one to the next, those are going to be supplementary. And the diagonals intersect at their midpoints. Okay, so that just means each one of these diagonals is going to get cut perfectly in half. They're going to be different lengths in terms of their total length. So MT here is going to be a little shorter than AH. But MT, where that diagonal hits at F, that's going to be the midpoint, and it's going to be bisected. So we're going to have the same length on both sides. So they're not all going to be 5, but these two are, and we'll get into that in a second. All right, so opposite sides are congruent. Opposite angles, like A and H, or M and T, are congruent. They're the same. Consecutive angles add up to 180, supplementary, and the diagonals intersect at their midpoints. So let's jump into this example. It kind of just walks through those basic properties of a parallelogram. So in this parallelogram, MATH at the right, they give you all this information. It's also labeled here in the picture. I think it's important. This angle, it's hard to tell. Is just this little piece, FHT, 80 degrees, or is the whole thing 80 degrees? So you have to look up to the given, basically. And they're telling you it's MHT, that's 80, all of it. It kind of looks like half of it's 80 in the picture. So just be careful. All of it is 80. So we're going to find these measurements. FM, right here, is the other half of this diagonal. The point of intersection of the diagonals is always the midpoint of the diagonals in a parallelogram. Okay, that is part D of the properties of parallelogram theorem. So if I know FT is 5, I know that MF or FM is also 5. Pretty basic. HT, the opposite side of a parallelogram, is always congruent. So if this is 8, this is also 8. Angle MAT, that's this whole angle. Opposite angles are always congruent. So if this one's 80, this would be the opposite one. It's also going to be 80 degrees. And then the angle HMA, these would be considered consecutive angles, this one and this one. So if this is 80, this one has to be supplementary with it, so add up to 180 degrees. So if that's 80, this must be 100 degrees. And if you want to show that, so when you look back, you can see it, it's 180 minus this 80. So these two consecutive angles all the way around, whether it's these two or these two or these two, they're going to be supplementary. They're going to add up to 180. All right. So using one of these properties now, we can always find the distance between two parallel lines. Because remember, a parallelogram is made up of opposite sides that are parallel. So they are parallel lines. Now, they might not always form a rectangle, a square, or just a basic parallelogram. But if we just have parallel lines in general, the distance between the two parallel lines is the length of a segment that's perpendicular to the lines and has an endpoint on each line. So basically, if I have two parallel lines, if I connect them with a segment and it hits at 90 degrees, it would hit at 90 degrees on both of them. That segment will be considered the distance between them. If we don't have 90 degrees in both spots, that would not be considered the distance between them. All right, so the distance between two parallel lines is constant. That is the parallel lines theorem. So if I know that this is 3, I can measure that anywhere between these parallel lines, it's always going to be 3. Parallel lines never get farther apart or closer together, so if you have the distance in one spot, you have the distance between them everywhere. All right, and the last property of parallelograms we want to talk about is its rotation symmetry. The parallelogram symmetry theorem says every parallelogram has twofold rotation symmetry, so it's been a little while since we talked about that, about the intersection of its diagonals. So when it says about the intersection, that's talking about it rotating around that as its center. Because remember, I could rotate it around a center out here, and it's going to spin around that. But we're talking about rotating it here where it just spins in place, so around its center, which is at the point that the two diagonals intersect. And remember, twofold, if you're talking about degree measurements, you take 360 for your full circle divided by 2 for twofold, and that's 180 degrees of rotation. That's the smallest rotation that creates symmetry. So basically, you're just flipping it upside down. It's spinning 180 degrees. So point A would spin all the way to C, point B would spin all the way to D, and it would end up looking like it started. Okay, so it flips once upside down. You basically have the same parallelogram you started with, and then you flip it 180 degrees again, and you end up right back where you started. All right, let's flip it over. So 7.8, we're going to continue to look at these properties, but we're going to look at it as the converse. So in the front, we talked about, okay, you have a parallelogram. Here's what's true about it. Now we're going to be looking at a shape that may be a parallelogram, but how do we prove that it actually is? So the big idea says using congruent triangles, certain figures can be proved to be parallelograms. Again, we're not going to dive into the triangle part of this, but the triangles that are created by the diagonals, if you if you run them through really long proofs, you can show that these actually are parallelograms based on these properties. So we're going backwards now. So you're given a shape. Is there enough information, basically, is what they're asking you. Is there enough information to prove that this is indeed a parallelogram? And so we're going through our A, B, C, and D again, but these do not directly reference the A, B, C, D in the other theorem. Okay, this is different. So these are the sufficient conditions for a parallelogram. If you see these things to be true, you are allowed to say this is a parallelogram. So if you can prove that one pair of sides, so we're not worried about the other pair, just one pair of sides, is both parallel and congruent, so they're parallel to each other and they're the same size, that's enough information to say, yes, that's a parallelogram. Or another option, B, both pairs of opposite sides are congruent, so opposite sides are the same length. We don't have to prove they're parallel. We just need to know that they're all the same length. And we have enough information to say, yes, it is a parallelogram. Yes, these are parallel to each other. Okay, so that's an easy one. If the opposites are equal, it is a parallelogram. And remember, this is talking about quadrilaterals, so you have a four-sided shape. The diagonals bisect each other. So if you have a four-sided shape, you draw the diagonals, or it's drawn for you, and you see that they're both cutting each other in half at the midpoint. That's enough to say, yes, that's a parallelogram. Or you can also look at the angles. And like we talked about on the front, opposite angles. So we're talking about across the diagonal. Opposite angles, if they're equal or congruent, then we know the quadrilateral is a parallelogram. So there's lots of different options of ways you can prove something is a parallelogram, A, B, C, and D. And so you'll see that today in your work as well. Okay, so 7.9. Now we're going to look at more than just parallelograms, and you can see we've got our hierarchy here specific to what happens with the diagonals. And these are going to be properties we've already established, but we're going to refer back to them now and talk about how we can use those properties to prove something is a square or a parallelogram or an isosceles trapezoid or a different quadrilateral. All right, so let's start with kites. So kites have a diagonal Notice it says a diagonal, not both diagonals. Kites have a diagonal that is the perpendicular bisector of the other. So here in the picture, if I draw this diagonal and this diagonal, the longer one we've talked about, that's not getting bisected, right? You're going to have a longer segment here than on the other side. But this one across, that goes across the symmetry line, that is going to be bisected, and they're going to hit at 90 degrees. That's the perpendicular bisector. So again, perpendicular means 90 degrees, and then the bisector means cut in half. Now, underneath a kite is a rhombus and a square. A rhombus is a very specific type of kite, and a square is a very specific type of rhombus and kite. So that means this must hold true for them as well. So one of their diagonals will be the perpendicular bisector of the other. Now, what's special about a rhombus and a square compared to a kite is actually that both of them are the perpendicular bisectors, and we've talked about that for a rhombus. They're both going to cut each other in half, and it's going to hit at 90 degrees. Same thing for a square, and that follows true because they're underneath the kite, but the kite just has to have one side that gets bisected, and they hit at 90 degrees. Okay, but these fall under those same properties as a kite. They also gain this property from a parallelogram, and that's what we just referred to. So what's special about a parallelogram's diagonals is that they bisect each other. So if I connect a basic parallelogram by the diagonals, I know that this equals this, and this equals this. So that's going to be true for a rhombus and a square and a rectangle. So in a rhombus, I know, because it's a parallelogram, that both diagonals are bisected, and because a rhombus is a kite, I know that this is also hitting at 90 degrees. A square, again, they are going to get bisected, and in this case, they're all going to be the same, and it's going to hit at 90 degrees. So the 90 degrees comes from the kite. One of them being bisected comes from the kite. Both diagonals getting bisected comes from the parallelogram. So rhombuses, rectangles, and squares fall under your parallelogram. So we can do the rectangle as well. If you draw the diagonals, they are going to be bisected. And those would be the same all the way around. All right, and then isosceles trapezoids have congruent diagonals, and that's kind of what I was getting at here with the rectangle and the square without getting ahead. So remember, not all trapezoids. Isosceles trapezoids, where these sides are equal, but base angles are equal, the diagonals are equal to each other. Now you can see these are not being bisected. You're going to have a lot shorter pieces up top, but the total length of the diagonals are equal. They're congruent, and that's why when you have a rectangle and a square, their diagonals are congruent because they fall underneath the isosceles trapezoid here, but they also get bisected. So if they're the same length diagonals and they get bisected, you're going to end up with 4 equal pieces. Okay, so the hierarchy explains everything we need to know. One diagonal gets bisected and it hits at 90 degrees. Everything under a kite makes that true. The diagonals just bisect each other. They don't necessarily hit at 90 degrees. Okay, that's a parallelogram. If they do hit at 90 degrees, that means it's a rhombus because it is both of these together. So it has a perpendicular bisector and both diagonals bisect each other. Proves that it's a rhombus. Okay, and a square falls under all of this. And so an isosceles trapezoid, the entire diagonals are congruent to each other. So a rectangle has that as well. Because a rectangle is underneath a parallelogram, those two equal or congruent diagonals also get bisected. So you get 4 equal pieces. And a square inherits properties from a kite, a parallelogram, and an isosceles trapezoid. So the diagonals are congruent, they get bisected, and they hit at 90 degrees.